Well, teacher, our group today has three members, is Lê Tiến Đạt, Nguyễn Hồng Sơn, and me, Đặng Thu Hà. And we're gonna present about our project named House Price Prediction. Our presentation have four parts. The first one is reason for choosing this topic, and the second is explanation of the technologies used in the project. The third one is the entire process of the software's operation, and the last one is practical application of the project in real life. And if you wonder why we're choosing this topic, well, there are two main reasons that come up in our brains right after we see the topic. The first one is house price recently continue to increase in many regions, and the second one is housing trends differ significantly by region. So predictive models can help identify trends and mitigate risk for potential homeowners and investors. The next part of our presentation is the technology we used in the project. The first technology is key libraries and frameworks. The second one is machine learning concepts. The third one is data handling technicals. And the last one is system environment. While the first part is key libraries and frameworks, we use pandas for data manipulation and analysis, such as handling dataset, cleaning and transforming data. NumPy for numerical computations, such as handling arrays and performing mathematical operation. Seaborn is for data visualization, helping to identify trends, correct correlations, and outlining. And then the second technology we use is machine learning concepts. We use multiple linear regression. It's for predict a target variable based on multiple predictors to assume a linear relationship between the independent variable and the dependent variables. And we use the chain test split, a technique to divide data into training and testing sets to evaluate model performance on unseen data. We also use evaluation matrix like mean squared error and R squared are used to assess model accuracy and explanatory power. The next technology we use is data handling technique. Data cleaning, handling missing or inconsistent values, outlier removal. Feature engineering, transforming raw data into meaningful features for the model, such as scaling numerical variables or encoding categorical data. We also use exploratory data analysis, visualizing data distributions and relationships to identify patterns and insights. The last technique we use is system environment, local or cloud-based Jupyter Notebook. The project is executed in an interactive Python environment, and the dependencies installed using tools like pip or Conda. The next part is process of the software operation. Our partner will continue this part.
Okay, as you can see on the screen, we have a code to importing library, and next we move to load the data set. You can read the housing data from a CSV file into a Panda data name. Next, explore the data. The first display the first 5 rows of the data frame to get a quick overview. Second, provide information about the data frame. And last, calculates the number of null values in each column. Next slide, we handle missing data. Remove rows with any missing values. This can be a simple approach, but it can lead to loss of information. More sophisticated technique like imputation or model-based technique might be considered in certain scenarios. The process the data. Remove the ocean proximity column as it might not be relevant to the house price prediction or might require complex feature engineering. And analyze the data. This provides summary statistics for numeral columns, such as mean, standard deviation, mean, mass, and this slide sets up the size of the plot figure using matplot fixed size specify that the figure will be 8 units wide and 4 units tall. And the SNS dot this plot DF median house value equal creates a distribution plot using the Seaborn library. And here is the diagram about distribution plot. And as you can see that this code will snippet generate a scatter plot to visualize the relation between median house value and longitude. First is configure the size of the figure to be 12 units wide and 8 units tall. The second data equal df. This instructs Seaborn to use the data frame df for the data. Each point represents a house or regions in the dataset. The position of the point shows the relationship between its price and its longitude. This code will create a scatter plot to visualize the relationship between median house value and latitude. Second, visualize how house price vary by latitude. And the last, detect trends or patterns such as whether houses in certain latitudes, north or south, are more expensive. This diagram shows you each point represents a house or area. The point's position reflects the latitude and its corresponding house price. And this code will generate a scatter plot where the geographical location of house is visualized and the house prices are represented by color to show regional variations. Second is colors the points based on the median house value column. And this one is visualized to geographical distribution of house prices. It helped identify spatial patterns, such as whether expensive houses are clustered in certain locations, for example, near coastal area or urban centers. Okay, so next that will continue the presentation.
Thank you, Cerns. And as you can see on the screen, this code is a Pearson correlation coefficient, and As you can see in the diagram, rows and columns correspond to the data frame's numeric variables, and the cell values indicate the correlations, coefficients between the two variables. Can you move to the next slide, please? Okay, and here's, as you can see, this code generate a heat map to visualize the correlation between different features in the datasets. And the darker the colors, the stronger the correlations. And these have identified features that are highly correlate with the target variable. And it can be useful for feature selection. Okay, and this is an example, the heat map. And in this heat map, rows and columns represent numeric variables in the datasets, and each cell shows the correlations, coefficients between the variable on the row and the variable on the column. And the colors of each cell represents the correlation value. And the diagonal cells always have a value of 1.0. It is a perfect correlation with itself. And as you can see in this code, we have a lot of code here, and most of the lines create a new data frame that contain all the features except the target variable, and it is the same. We use exchange and test at the end to scale the testing data using the same scalars. And here's the model building. The model, this model create a sequential model, which is a linear stack of the layers. And as you can see, it's like the rest of the model is comply the model with the ADAM optimizers and mean square error, or you can call this MSE loss function. In the next section is model training. This line create an early stopping callback, which stop the training process if the validation loss stop decreasing. And in the below line, train the model using the training data with validation data for monitoring performance. And this patch size is 128. The maximum numbers of the epoch is 400. And the early stopping callback is used to prevent overfitting. Here's the model training and evaluations. In the left side is the code extract the training history from the model 1 object into a data frame. And this history includes metrics like loss and validation loss for each epoch. And the rest is the loss. And this loss, the loss and validation loss over the training epoch. This plot helps visualize how the model's performance improves during training and whether overfitting occurs. This slide calculates the mean absolute error, MAE, between the true values in y-test and the predict value in the predictions. MAE measures the average absolute difference between the predict and actual values. And the below line is the line we use to calculate the root mean square error between the true values in y-test and the predict values in predictions. RMSE measures the average square difference between the predict and the actual values, and then takes the square root to bring it back to the same units as the target variable. Okay, so we have talked about the technologies and the operations of the course. So here is the final part of our presentations is the practical applications of the projects in real life. And I think that with the house price prediction code we have today, we have some, like practical application for this. The first is for homeowners and buyers. With accurate price predictions, it helps homeowners and buyers make informed decisions about buying, selling, or refinancing their homes. And understanding the market value of a property ensure fair deals for both buyer and seller. And predicting future price trends allow homeowners to plan for potential increase or decrease in their property value. The next application is for real estate agents and investors. And real estate agents can use price prediction to set appropriate listing price and attract potential buyers. Investor can identify profitable investment opportunities by analyzing predict price trend in different markets. And finally, investors can optimize their real estate portfolios by understanding the potential returns and risks associated with different properties. And finally, is the benefit for policymakers. Accurate price prediction can help policymakers make informed decisions about land use, infrastructure development, and housing policies. And by understanding housing market trends, is crucial for overall economic forecasting and policy making. And finally, policymakers can use price predictions to allocate resources to affordable housing program effectively. And in conclusions, by understanding the factors that influence house prices and using advanced analytical technique, we can make more informed decisions about real estate investment and transactions. That's the end of our presentations. Thank you for listening.